you very much. I'll dim the lights very slightly. So thank you very much. This is the most extraordinary thing to be doing. I would never have imagined in 2004 when I arrived at BSMS I'd one day be delivering an inaugural lecture. I cannot tell you. I would also never have imagined the journey that took me here. And in trying to decide what on earth to say to you for the next 50 minutes, I thought what I'd do is just try and tell you that story really, because it is quite instructive. It's a story really about how the patients that I'm involved in looking after at the hospital have laid out this path in front of me really, which by following has resulted in the development of a clinical service, a clinical training scheme and a body of research where there was really nothing like this in Brighton before. I will try as I go along and thank all the important people who are individually responsible for bits of this, much more than I am myself. I hope I don't forget anybody. But before I start, there are 4 people who are not in the room that I want to, I wish were in the room for various reasons. So my parents both died many years ago, a number of years ago. My father, as you can see, was a doctor. I'm not sure he was a role model as a doctor. He always said he went to medical school at 17 because it was the earliest course you could start. So to get out of South Wales, he went and did medicine. My mother, as you can see, was much later a nurse, but she left school at about 16, and after nursing much later in life, did a Bachelor of Arts degree, got a first-class degree in her 30s, and certainly put in my mind the idea that learning stuff is not something that stops when you're young. And that's a very important thing, I think, for life in medicine and academia. This is Graham Ailiff, my father's dear friend and fishing companion, who was also, unbeknownst to me as I was growing up, a professor of bacteriology at the University of Birmingham, and was actually pioneering what was then a very a backwater really of research, which was healthcare-associated infection. And his research laid much of the groundwork for the field I found myself working in today. And sadly, he died earlier this year. But I'm enormously honoured that his wife, my godmother Janet, has made the journey down from Birmingham to be here today. And then this gentleman, every bit as malignant an individual as he appears, this was my junior school headmaster. Who at the age of 8 in public told me that I should concentrate on singing and playing rugby because I was never going to have a career in academia. Maybe a motivational speaker. So even before I was born, infectious diseases had been consigned really to the history books of medicine. So this quote's probably made up actually, but it's very widely said. And if you look at what was happening with infectious diseases in the 20th century, you can see why people would have thought this. So this graph just shows the disappearance of those major infections that stalked industrial humanity in the 19th and 20th centuries. There you are. Measles, scarlet fever, typhoid, whooping cough, disappearing throughout the 20th century. And it's sometimes helpful to describe these sorts of germs as professional pathogens. This is a term I'm going to use a little bit this evening. I use in my teaching. These are germs that can make healthy people sick. They don't require you to have anything wrong with you. They are not normal human commensals. That means a germ that lives happily, normally with you without causing any harm. And they're transmitted predominantly during disease, and they're a special subtype of all the germs that we encounter, really. This is a nice aerial photograph of Brighton's own infectious diseases hospital, built in 1891, funded locally to deal with the epidemics, particularly of scarlet fever and TB at that time, and you can see why it closed in the 1940s. And at this site now, there is simply a housing development and a small HIV centre at the Sussex Beacon. That's all that remains really of that site. So when I arrived at the London Hospital, it wasn't even royal in those days, not a great centre of academic excellence, I think, at least at that time. It was good for microbiology, though, to be fair. In 1986, I certainly didn't have much idea about infectious diseases. I can't particularly remember what I was thinking about. I think it looks as if I'd given up rugby by the look of it, but the singing possibly was still going on. Enough of that. Anyway, my interest in medicine, such they were critical care, really. And I, about 10 years later, pursuing a career in critical care, found myself to this place to do ITU, and I wondered if anyone can recognise this. Bit of audience participation. Exactly, well done. So this is a still from the film 28 Weeks Later. So this is Jim, who has just taken his own discharge from the intensive care unit at St Thomas's Hospital. There he is, making his way across Westminster Bridge. And he has, thematically in the film, of course, not caught the virus, which has turned the rest of humanity into zombies. And what I learnt working on the intensive care unit at St Thomas's, that this was a good critical care outcome. because one of the greatest threats that intensive care patients face is infection. And it's really brought it home to me that I needed to learn something about microbiology, how to diagnose, how to treat infection, if I was going to be able to help patients really at the sharp end of modern medicine. And this took me on the next stage in my journey. I was reading lots about this stuff, and I kept coming across the name of this bloke who worked at the Hammersmith. And so with all the enthusiasm of the young, this is not a cool story, but I'm going to share it with you briefly because it's instructive. I wrote to him. Cohen was his name, and he's written file, Katie noticed on this letter, but he did decide to actually respond to it rather than just file it. And to his enormous credit, John saw me, gave me some advice about my career. I don't tell students this story, but I do tell students how important it is to contact someone you think you might want to work with, have a conversation with them. If they speak to you, great. If they don't, bother with them. If I forget about them, it's not worth it. And certainly welcoming young people, I think, is a hugely important part of academia and medicine. So there you are. I've read with great interest the work published in your department, much of relevance to my current clinical practice. Nauseating. Move on. Anyway. So I went off around North London, where infectious diseases were certainly not dead, and there was a certain amount of TB around, and I published my first paper on tuberculosis, a good old professional pathogen. This paper is notable really primarily for its footnote. We'll hear more about Katie later on. She's certainly never been referred to as Catherine again. It appeared in that paper. And then I went back to the Hammersmith Hospital to do my first period of research and encounter the one and only professional pathogen I'm going to tell you something about. And we've had a project in my house this week. The children have been doing altering bacteria. So Ewan has got strep pyogenes. Hold up strep pyogenes, Ewan. There it is. What do you notice about it?
Red, holding a knife and fork.
Yeah, so it's holding a knife and fork. It probably ought to be blue, actually, but it's holding a knife and fork because it's the flesh-eating bacterium. So it's called this because it rarely causes this horrible disease called necrotizing fasciitis. I'm not going to show you pictures of that because it's really grim. But it is a major professional pathogen of man, and it causes common, mild, usually sore throat, strep throat, the syndrome of scarlet fever I mentioned earlier on in children, common cause of skin and soft tissue infections. It causes, rarely, as I say, these nasty, invasive and toxin-mediated infections, and very rarely it causes these fascinating post-infective immunological sequelae, particularly this thing called rheumatic fever. And so this illustrates one of the core questions in infectious diseases research. What determines the different outcomes you get after a patient has infection with the same organism? Is it special things about the bug? So I'm getting carried away. Special things about the bug? Is it special things about the patient, their genetics or their underlying disease? Or is it things to do with the treatment that they've received? And I was interested in the patient, and I did a nice piece of research funded by the MRC. I got a nice paper. I got a PhD, yay. I got a job down here at Brighton. And my head was full of how I was going to research the immunopathology of this fascinating disease called rheumatic fever. And somebody, I think it might have been Kevin, said to me, "Do you see much rheumatic fever?" So this is a disease which really ceased to be a problem for the NHS about the same time the NHS was founded, actually. So important and interesting, and so what I encountered when I arrived in Brighton, which changed the whole course of things, was Staph aureus. So who's got Staph aureus? Emily? You've got you've got C. diff. Sit down, man. You've got Staph aureus. So what do you notice about Staph aureus, Emily? It's balls. It's got a cape. It's got the cape. Polly made the cape, and it's got a cape. Thank you. It's got a cape because it's a superbug. So Staph aureus is commonly called a superbug, but the point is it's not a superbug. Staph aureus is a commensal. It's an organism which lives harmlessly with us. It's transmitted between us in states of health, in our homes, in schools, in gyms, wherever we live. It can be transmitted in hospitals, but not usually during the diseases that it causes. But it will cause diseases given a chance, and so it's an example of an opportunist, a commensal opportunist. So as you sit in the audience, about 50% of you will have Staph aureus sitting harmlessly up your nose. If you were to swab your nose, you'd find it sitting up there. But it also is very able to take advantage of the opportunities modern medicine offers, so it can infect any plastic work. This patient's got a plastic line given in for drugs, and this has become colonized by Staph aureus, and it's creeped into the bloodstream flowed around the body in the blood, causing what's called bacteremia or bloodstream infection. And this is an MRI scan of someone's spine, and you can see this vertebral body here and the disc which has become infected with Staph aureus. And in addition to these alarming, aggressive, invasive sort of bloodstream infections, Staph aureus is the leading cause of surgical site and orthopaedic device infections. It was discovered, therefore, you won't be surprised, by a surgeon, a Scottish surgeon, Ogston, and he was examining pus from his patients. He found they had these round organisms grouped in clusters. And he called them Staphylococcus because they looked like bunches of grapes. And he called them Staph aureus because when you grow them in the laboratory, they have this lovely golden sort of colour. The point of telling you all of this is that this is still fundamentally, with a few bells and whistles, how we identify Staph aureus in the laboratory today. But it belies something which is very important and we've come to understand over the last 10 years or so, which is that actually what we call Staph aureus is hugely genetically diverse. So about 25% of the genome is variable between different strains. And one way that that variation impacts, of course, is MRSA. You'll all have heard of MRSA, particularly if you're a bit older, because this was a huge medical problem back in the 1990s, early 2000s. This graph shows the emergence of MRSA as bloodstream infections initially reported voluntarily and then reported through a mandatory scheme, peaking about the time I was arriving in Brighton, 2004, 2005, 7,500 cases of this. There were at least as many methicillin-sensitive cases and a huge burden of other sorts of Staph aureus infection. And another way that this genetics played out is that, interestingly, 95% of these cases were caused by just 2 clones of Staph aureus. I'm going to give you the names of them because I'm going to come back to these names in a second, so-called ST22 and ST36. Now, nationally, as I say, we were seeing, in the UK at that time, there were about 16,000 cases of Staph aureus bacteremia, so we in Brighton would have expected to see about 10 a month, and at those days there was no ID service here. John and I used to do ward rounds with our colleagues in microbiology, and we were seeing about 30 cases of this disease a month. It was really striking that we were seeing, it was basically all we saw initially. The rates had risen very dramatically over about 2 years, despite the fact that Tony Blair had introduced a target for all trusts to reduce their MRSA rates. So everyone was working flat out to get rid of this disease, and the rates were going up. We were also seeing a really striking rate of these complicated Staph aureus infections, and I was seeing things I'd never seen before. This is a CT scan of a patient's abdomen. These are the kidneys, and this is a big abscess sitting in this patient's left kidney caused by Staph aureus. So we were seeing disease that was more common and more severe, and this took us back to the sort of question that I told you about for my PhD. So why is Staph aureus doing this? It didn't seem there'd been some change in the patients in Brighton. It didn't seem that there'd been any change in the way the patients were being managed. Could it be there'd been a change in the strains of Staph aureus that were causing the infection? So this graph just shows a little more detail about what was happening. So these were our old bacteremia rates, fairly normal, shot up around 2004 in Brighton, when these all other hospitals in the region were going down. So we did a really simple experiment. We got some isolates out of the freezer, and we got some isolates from now, and we typed them. So we did what's called sequence typing, which is the best typing at the time. As expected, 95% of the ones from before the outbreak were these 2 dominant sequence types. Rather disappointingly, so were the ones from the outbreak. So researchers' greatest fear, an experiment that shows you something that you didn't want it to show you. And for me to explain what that means and how we went forward, I just need to tell you a little bit more about how we tell bacterial strains apart. So we used this thing called sequence typing, multi-locus sequence typing, which was the best available thing at the time, as I say. It had been invented partly here, actually, by Brian Spratt, who worked at the University of Sussex, just next door, and relies on the technique of DNA sequencing. So reading individual nucleotide letters in pieces of DNA. And what MLST does is look at 6 so-called housekeeping genes, so genes of Staph aureus that are always present in all strains, sequences those, lines them up and says, well, look, if they're all the same, we'll call them the same sequence type. So that sounds great until you realise that what that actually means is you know that less than 1% of the genome of the organism is actually the same. So the rest of the organism has the potential to be very different. So you may say, well, why didn't we sequence the whole genome? Well, the answer is because it was so ridiculously expensive and slow at that time. So you may remember, I think probably everyone will have heard of the Human Genome Project, which in 2003, so a few years before we were doing this work, had published the first complete human genome cost around $3 billion. By the time we were doing this study in 2007, the cost had come down. So Roche, with great aplomb, presented James Watson of Watson and Crick fame with his own genome on a memory stick. It cost them $1 million to do that. So it was still jolly expensive. But this heralded the era of what was known as the quest for the $1,000 genome, the idea that if technology could advance and give you a human genome for $1,000, that would be a real game changer. And through my colleague John Paul, more of whom in a minute, we were put in touch with a group in Oxford called the Modernising Medical Microbiology Group, led by Derek Crook, who had a simple but very brilliant idea that if you were going to be able to sequence humans for $1,000, bearing in mind how cheap, what smaller bacteria are, you're going to be able to sequence bacteria very cheaply. So we went back to our bacterium isolates. This is James Price. I was about to call him Harry Potter there for a second. Sorry. This is James Price, who came as a trainee, one of the first trainees at that time, and he set off to do a very simple experiment to sequence these isolates instead of having done the sequence typing as before. So there's a few scary graphs in this talk, but not many, and this is clearly one of them. But it's not that scary. These are family trees. So a family tree of the ST22 MRSA and a family tree of the ST36 MRSA. And the Brighton isolates are in red and the Oxford isolates are blue. And the distances from tip to back out again are genetic difference, basically. And so what you're meant to notice is lots of diversity in this family, both before and after the outbreak. But in this family, this tight little clone of highly related organisms that look around 2004 at the time of the outbreak. So this had told us something we'd never expected from the existing sequencing. Not a massive scientific breakthrough, but we learnt that whole genome sequencing is a huge step forward and really has the potential to do some very clever things for our research, particularly through its ability to distinguish genomes down to a single DNA letter. The term we use for this is a SNP, a single nucleotide polymorphism. So you can take two bacteria, are they identical? If they're not identical, how many SNPs differentiate them? And if you know roughly how often bacteria make mistakes, put different SNPs in their genome, then you can work out how long it is since they had a recent common ancestor. What did we gain from this? Well, we gained collaboration with leading sequencing and bioinformatic researchers, access to expertise and funding that as a new medical school with no track record in this research we couldn't possibly have had, and the ability to start doing some studies that would really benefit our patients. So I'm just going to very quickly in a few slides tell you some detail about one particular study, which is the study that James did for his PhD. I'm mainly going to tell you this because he's a wizard with PowerPoint, and so these slides are his slides and they're really tremendous, so I can't take credit for them. So he was setting out to investigate Staph aureus transmission in hospitals. The background to this is that hospital staff clearly work very hard to prevent patient transmission of Staph aureus, but sometimes patients catch Staph aureus in hospital. And the question was, do people acquire it because of failures to prevent transmission? And can we use sequencing to investigate outbreaks? And I should acknowledge Drew, who was the nurse on this study, without whom it could not possibly have happened, and John Paul, I've mentioned, you can see, one of the country's most esteemed microbiologists. So the study was conducted back on intensive care. Over 14 months, James and Drew screened all the admissions, all the discharges, and weekly in between. In total, he sequenced 273 Staph aureus isolates and used this SNP difference to infer likelihood of transmission. This figure just starts off by showing you the isolates we got from individual patients who were sampled multiple times, either between sites or over time. And what I want you to notice is there was very little diversity. These are SNP differences, mostly less than 10, or less than 30. And because we know how often Staph aureus makes these SNPs, we know that this equates to about 5 to 10 years of evolutionary time for these organisms to have been in these individual hosts. These are the data from the Staph aureus isolates that he got from separate patients. So first of all, I guess to point out they're very different, aren't they? Most of them are hundreds or thousands of SNPs apart, so decades of evolutionary time apart. And if you look at the acquisition isolates, those are people who caught or appeared to have caught Staph aureus on the intensive care unit, only actually 7 out of this 40 or so actually were related closely to another Staph aureus that had been found in a patient at the same time, which is kind of surprising. Interestingly, a small number of people had very similar Staph aureus isolates when they arrived on the intensive care unit, which makes you think there may have been some sort of contact beforehand. So do people acquire Staph aureus because of failures to prevent transmission? Well, on the whole, no, which is interesting. Second question, can we use sequencing data to investigate outbreaks? So this slide shows all the patients, 17 of them, who were ever in the study found to carry one of these MRSA strains, the ST22 one. And it looks complicated, but it isn't. So the first line shows when the patient was admitted to hospital, this is time, their pre-ITU stay, their admission to ITU, their time on ITU, their discharge from ITU, their time in hospital, and their discharge from hospital. And the dot shows when they were found to have MRSA. And so for most of these people, they were found to have MRSA actually when they arrived on the intensive care unit. But 5 patients appeared to acquire MRSA while they were being followed up on the unit. So they came in negative, became positive for MRSA. And 3 of them acquired MRSA quite close together in time, and indeed overlapped all of them with the ITU stay of this person, patient J, and who actually was admitted with MRSA despite the fact that his dot is there. And this, you might imagine, suggests an outbreak. So some patient-to-patient transmission of MRSA has occurred in that time. So using the sequencing data, what James did was to create a tree. This is a different sort of tree than I showed you before, because we're not trying to find an ancestor, we're just looking at relationships. And if you start by putting, you see the great PowerPoint, if you start by putting the isolates that people came into ITU with on the tree, you can see they're distributed all quite a long way away from each other. This is the one that might have been the source of the outbreak. If you then put the outbreak isolates on, 2 of them are genetically a long way away from anything else. These distances look small, but they're about 100 SNPs, so many, many years of evolutionary time. One of them is exactly the same as the putative source isolate. So at least one of these people, there probably has been a breakdown of infection control. Looking at the other 2, one of them is miles away from everything else, but then this last character up here, patient Q, had an isolate of MRSA which was genetically indistinguishable from a patient who'd been on the unit 2 months earlier, suggesting transmission had happened even though the patients had never been in contact with one another. So do people acquire Staph aureus on the whole? No. Can we use sequencing to investigate outbreaks? Absolutely yes. But it begs the question, where do these people catch Staph aureus from, if not from each other on the unit? So James went back and did an even more systematic evaluation. This time he screened not just the patients, but the nurses, the doctors, the physios, and the environment. And he sequenced all of these isolates and called anything that was in 40 letters of each other one subtype and assumed they were the same and they were involved in some transmission. And what did he find? Well, in contrast to what you might expect, you might imagine on an intensive care unit, particular strains of Staph aureus may get passed around from patients to doctors to the environment. What he found was that every month, on average, 38 new strains of Staph aureus arrive in the intensive care unit. So more than 1 a day. And indeed, if you plot these out, this is a scary looking graph, but it's just time, and each one of these is a new subtype appearing on the unit. They keep on appearing over the duration of the study. So it's not as if you're just saturating or exhausting a population and eventually it tails out. They keep on coming, these new subtypes of Staph aureus. Most of the time, healthcare workers carry a Staph aureus, the same as all of us, they've got it up their nose, but they almost never give it to a patient. Even though we clean the unit very carefully, if you look hard enough, you can always find Staph aureus on the intensive care unit. But it comes from the patients and the staff, they don't acquire it. Of 92 patients who acquired Staph aureus, 4 caught it from healthcare workers, 2 from the environment, 11 from other patients, and 80% of them didn't appear to have caught it from anywhere. And I'll leave that hanging for just a second, and we'll come back to it in a couple of slides when I've finished a few other things about Staph aureus. Because obviously we had a lot of fun with sequencing in Staph aureus, but Staph aureus and getting involved in Staph aureus research transformed our work in Brighton in a number of different ways. One of the things that may surprise you for a disease as important as I've told you Staph aureus is that back in 2006 there was really very little evidence to guide us as doctors as to how to treat patients with Staph aureus bacteremia. 16,000 patients every year in the NHS, only 1,600 patients in the world ever had been randomised to clinical trials to tell you how to treat those patients with Staph aureus bacteremia. And this reflects the fact that people have only recently woken up to these as important pathogens. So we started off doing some local observational studies to inform our own practice. One of our first registrars, Guy Thwaites, set up a national network which still runs from Brighton called the UK Clinical Infection Research Group. He's now in Vietnam, heading the Wellcome Trust Centre there. We undertook national observational studies. We wrote some clinical management guidelines in Lancet Infectious Diseases back in 2011 from the evidence there was. We teamed up with international researchers to do matched up studies in Germany initially and then subsequently in Denmark and South Korea and North America. Guy and the UKERG group secured funding for the largest trial ever conducted in Staph aureus bacteremia, the ARREST trial, which recruited 770 patients to inform the management of this disease, and that finished this year, and that paper has just been accepted in the Lancet and will come out later this month. And this year, I'm really pleased to say the two big international infectious diseases societies, ESCMID and the IDSA, partly driven by this growing body of evidence that's coming out of these collaborations, has commissioned guidelines for the first time in Staph aureus bacteremia in preparation for 2019. We've also used these clinical studies to inform some basic science research, in particular in the field of what are called genome-wide association studies. And you'll have heard of these in the context of human genome-wide association studies, probably. These are studies where you get thousands of patients who have diseases like hypertension and diabetes, and you compare their whole genomes to thousands of patients who don't have those things, and you say, well, what are the genetic bases of those diseases? What we've been able to start doing now, because we've built up these enormous cohorts, is to start doing bacterial genome-wide association studies, using thousands of Staph aureus strains from these studies to look at associations with carriage, disease, between different forms of disease. And just to show you as a cartoon how this works. So human genome-wide studies have been done actually in North America, so not by us, comparing asymptomatic carriers, look, he's got Staph aureus up his nose, with people who've got invasive Staph aureus disease. And there are no human genetic associations with invasive disease like that, which is interesting because professional pathogens usually do have host genetic components. Maybe these opportunists don't. We've done studies in collaboration with Danny Wilson and Bernadette Young in Oxford and with my colleague Achim, I mentioned before, in Germany, to compare the strains of Staph aureus from people's noses to the strains of Staph aureus that cause invasive disease. And we find no genetic basis for invasive disease in that way. We've also done a set of interesting studies comparing patients with different sorts of invasive disease. And the answer there is that for some sorts of invasive disease there's a genetic link, and for others there isn't a bacterial genetic link. The last experiments we've done are really fun, which are to compare the Staph aureus isolates from people's noses with the Staph aureus isolates causing invasive disease in that particular individual patient. And extraordinarily what we find is that Staph aureus evolves inside us, and you get within host evolution, so you get separate populations forming in the nose to the populations that appear inside the body. And you might imagine that those organisms are selecting mutants that make them more aggressive and cause more invasive disease, but they don't. They select mutants that make them less aggressive and adjusted for within host persistence. And this may explain that missing 80%. Maybe they all actually had Staph aureus persisting inside them before re-emerging on the ITU. And this is also an area where a recently joined PhD student, Kevin, is now looking to develop this for diagnostics. That's enough Staph aureus. Who's got C. diff? Ben's got C. diff. You've got C. diff? Wake up time. What do you know about C. diff, Ben?
It's purple and it's shaped like a drumstick.
Yep. And it's got a cape. You've got to mention Polly's cape. So it's thank you. It's purple, it's shaped like a drumstick, and it's got Polly's cape. It's another non-superbug. So the paper's always called C. diff, a superbug, but again, it's not. It's a normal commensal that lives in your intestine. And down the microscope, it looks like this. It has this drumstick appearance that Ben showed for us because it can produce these things called spores, which are like seeds and can be very important for infection control purposes. But C. difficile is a normal commensal. All children have C. difficile in their intestines. They lose it by the time they're about 10. It returns in adult life and old age. C. diff is intrinsically resistant to some antibiotics, makes spores, and can be transmitted in hospitals. And it's been a recognised cause of diarrhoea really since the 1990s. Elderly people given antibiotics, kills the good bacteria, C. difficile overgrows, produces some toxins, diarrhoea, and usually a pretty mild disease, historically with a very low attributable mortality compared to things like Staph aureus bacteremia, for example. But a very similar thing happened with C. diff in the NHS to what happened with Staph aureus. So this is a graph showing the incidence of C. diff in the NHS going back to the 1990s. I remember my interview at St Thomas's in 1996 being asked if I'd seen much C. diff, but it was beginning to emerge at that time. And you can see by 2006, huge numbers of cases, but mostly pretty mild, so people didn't particularly care. But then something pretty extraordinary happened. So these are data from the Office of National Statistics and show death certification data and show that C. diff started to appear in a very dramatic way on death certificates around that time. And what had happened is that around the year 2000 in Quebec, a new strain of C. difficile called the O27 strain had appeared, a strain that was both more virulent and resistant to certain types of antibiotic that were used a lot, particularly in North America at that time, quinolone and cephalosporin antibiotics. This spread in America, crossed the Atlantic, crossed the Pacific, and arrived in 2003, 2004, multiple times, probably in the UK, started to circulate around the UK. And those of you who have got involved in this for a long time, with long memories, will remember big, notorious outbreaks at Stoke Mandeville Hospital and at Maidstone Hospital, not far from here, just up at Tunbridge Wells, Maidstone Tunbridge Wells Hospital. And these were investigated by the Healthcare Commission, lots of cases, but I also want you to notice this, very significant attributable mortalities that we were not familiar with from C. diff. And to its credit, the hospital in Brighton engaged very proactively in this. And during 2007, Mel Newport and myself and John were approached about the possibility of opening a ward to care for C. diff patients. And clearly we did this with open arms, and they had an idea that they wanted this to be a ward for infection control purposes. I'd point out they gave us this little ward at the top of a building that was actually built before the Bevendine Hospital, if you noticed, but anyway, never mind. 11-bed ward, one single side room, but it was our own ward. The first time Brighton had had an infectious diseases ward since 1948. They gave us a dedicated team of doctors and nurses. We were able to develop an evidence-based treatment pathway for these patients, and we introduced an institution-wide antibiotic policy restricting these classes of antibiotics that were associated with C. diff. And this was completely transformational for developing a clinical service and training and research in Brighton. Our trainees for the first time had experience of direct patient care. We secured funding for interventional and observational studies to improve the outcome of these patients. Here are some of the people who joined us at the time. Vari and Kate Nambiar both joined initially on industry funding. Kate went on to do her PhD around C. diff immunology. Jazz we poached from geriatrics, I think it's fair to say, but has stayed and did a PhD on C. diff and subsequently on AMR. And this is Laura, who recruited 500 C. diff patients to her study, research nurse, 550 C. diff patients to a study, which published finally just this year. And this allowed us to produce what I think is a tremendously creditable set of clinically based, largely observational research studies. And I want particularly to draw attention to this one. We had the opportunity to be part of a large international phase 3 study for a new antibiotic, fidaxomicin, which is now licensed and used for treatment for C. diff globally. But the particular C. diff study that I want to tell you about for a moment or two is this one, because it's not high-tech, it's not clever, doesn't have any scary graphs of sequencing. It was simply an attempt to document robustly and report robustly what we were doing to try and show whether it made a difference. And so we were able to gather data through 2007, so before the ward opened and for the year and a half afterwards, first of all to show that we had actually dramatically changed the use of antibiotics in the organisation. So you can see we got rid of cephalosporins and quinolones very substantially, and we switched to old-fashioned penicillin-based antibiotics. That was associated with a sustained and very significant reduction in C. difficile rates over the following 18 months, and was also associated with substantial impact on the mortality associated with severe disease in these patients. Really simple observational study, but reported in a way that people could read it and make a judgment whether they wanted to do the same things in their own practice. And I'm pleased to say this has been cited multiple times now in national guidance in the UK and elsewhere as a piece of evidence that this is what you should do to try and control C. diff. The problem with all this, and researching healthcare associated infection generally, is that after a while you do yourself out of a job. And that's the problem. So this is what happened with C. diff and MRSA in the UK. And so you can see by about 2013, these diseases had substantially disappeared. And I always at this point make the point that we should be extremely proud of this, because no other healthcare system in the world has achieved this. It really is an extraordinary thing that the NHS managed this by working in a coordinated way, applying the sorts of things in Brighton we were doing everywhere. But the trick with medicine and infectious diseases generally is that the patients will always come up with something else that you didn't understand and need to address. And what the patients came up with was this: the emergence of antibiotic-resistant E. coli. And you can see the dramatic rates increasing in bloodstream infection from E. coli through this last decade up to this year, and the enormous increase in resistance to this drug called coamoxiclav, which many people in the room will have taken. It's a first-line oral antibiotic used in primary care for treatment of many infections, but particularly E. coli infection. Polly, your turn, you're up. So E. coli, what's it doing? It's eating an antibiotic. So Polly's been hard at work with her sewing this week and has created an antibiotic-eating E. coli. So E. coli live, they are commensals, of course, in your gut. So every time you take antibiotics, you feed them to the E. coli in your intestine. So the E. coli in your intestine, like little Timmy, grow up to be big and strong antibiotic-resistant bacteria. Clearly, MRSA and C. diff, in a way, are antibiotic-resistant bacteria, but the issue here is really much wider than that. We're talking here about antibiotic resistance in this very large and loosely grouped family of bacteria we call gram-negatives, because they're pink rather than the purple ones. And they include really important species like E. coli and Klebsiella species, which are normal commensals, again, of your gut, but also species of Pseudomonas and species of Acinetobacter that live in the environment. And all these germs have the ability to cause opportunistic infections, and really interestingly with E. coli, particularly in the community. These are no longer really hospital-associated infections, but really community-associated resistant infections. So Deborah said at the beginning about all the stuff that you read in the paper, and it's really hard to outdo this in trying to attract people's attention to this subject. Dame Sally Davis just does it all, really. So a ticking time bomb, the threat of antibiotic resistance, it's been described as a risk as big as terrorism, and this week again, an antibiotic apocalypse. The O'Neill report, which was commissioned by the last government to look at the economic impacts of AMR, has said if we don't act, by 2050, 10 million people a year will die due to antimicrobial resistance. But I think quite a few people now are beginning to think that this sort of hyperbole, combined with people saying, well, it's all to do with giving antibiotics to pigs, particularly Chinese pigs, it all makes it feel like somebody else's problem. And this can distract from the fact that there are really important things that as individual doctors and individual patients we should be doing to think about antimicrobial resistance. And I think one of the really important messages which has emerged in recent years that is really not yet getting across is, for the first time, we're beginning to be able to understand that antibiotic prescribing and consumption really affects negatively individual patients. So, for example, according to PHE data, there are more than twofold differences in antibiotic prescribing between NHS general practitioners. So GPs have very different thresholds for when they will give a patient antibiotics. I'm involved in a very nice study in Oxford at the moment, which is not yet published, but is linking antibiotic resistance in patients admitted to hospital with their GP prescribing practices. And what you can show is that if you're a patient of a GP that prescribes more antibiotics, you are at greater risk of antibiotic resistance yourself. You can also show that patients who take antibiotics, individual patients who take an antibiotic for a respiratory or a urinary infection, are at increased, substantially increased risk themselves of resistant infection for at least a year afterwards. That's as long as people have looked. And it's very clear that the more the exposure, the more the risk. The more courses, the longer the courses, the more the risk. So how much could we cut antibiotic use to try and avoid this? So different authorities, these are American data, estimate 30% of antibiotic prescribing in to humans is probably unnecessary. I was at a meeting last week with the director of the WHO. AMR theme used a figure of 50%. The former leaders of the United States and our own former Prime Minister have both committed our healthcare systems to reducing antibiotic overuse by 50% by 2020. So we have to achieve very substantial reductions in antibiotic use. And it's really unclear at the moment how we can achieve this, because I think there are only two ways of achieving reduced antibiotic resistance. One is, don't start the patient on antibiotics. And this is a common scenario from primary care. Patient comes to his GP, it's a virus, go away. And this is a safe and effective strategy in primary care. It's recommended by the government through its target toolkit. The risk of failing to treat life-threatening infection is low in primary care. Patients increasingly understand that common syndromes are actually viral, they don't need antibiotics, and you get really good positive feedback. So patients get better anyway, they know next time they got better without an antibiotic, and that's a great thing. The problem is in hospitals, it's a non-starter, because in hospitals patients are very sick. And in hospitals, you have initiatives like Surviving Sepsis, and I'm sure you've also read the other headlines in the papers about sepsis all the time, saying you've got to give patients who are ill broad-spectrum antibiotics within 1 hour, otherwise they're at risk of death from sepsis. So in hospitals, we have to use a different strategy, which is we have to stop antibiotics more often, sooner. And the way that we're meant to do that is by a process of review and revise. So that basically means we go back and see the patient over and over again and keep asking the question, is infection the right diagnosis? Is the patient getting better? Is it time to cut back or stop? Carrying out a daily risk-benefit judgment for individual patients. And this is called Start Smart, Then Focus. This is what we have to do. PhD tell us to do this. Start Smart means give prompt, reliably active antibiotics. Bearing in mind you're worried about resistance, that basically means last resort antibiotics, as the newspapers always call them, for any patient who might have a life-threatening infection, and then go back and try and change your mind through focus. The problem is that stopping antibiotics is really hard to do. So the NHS recently had a quality improvement initiative, it's ongoing actually, it was introduced last year, which assessed review and revise in hospitals. And it found that yes, 90% of the time, at almost all hospitals, someone goes back and reviews the prescription. That was achieved because the hospitals got money to achieve that. So they had to get 90%, so they did. But actually, when you looked at what happened, only, on average, 8% of those prescriptions were ever stopped. At some hospitals, it was as low as 2%. At some hospitals, it was as high as 40%. But across the whole NHS, it was, on average, 8%. And we did a study a few years ago which looked at antibiotic policies around Start Smart and Then Focus, and demonstrated that in hospitals that were big on the Start Smart and weak on the Focus, you actually end up with more unnecessary broad-spectrum antibiotic use and more C. diff and more potentially antibiotic resistance. So why is it so hard to stop antibiotics sooner? And there are many reasons for this, but I wanted just to talk for a few minutes about the problem of antibiotic courses. So antibiotics are traditionally prescribed in courses based on the illness a patient has. The problem is the course durations we generally recommend are probably longer than most patients actually need. And we back it up when we give them the courses by saying if you don't complete the course, you're going to put yourself and everybody around you at risk of antibiotic resistance. So what's the evidence behind antibiotic courses? You might be shocked to know this, that most of the antibiotic courses that people recommend were made up. They were made up in the 1950s and 1960s by experts who wrote books saying, I treat this infection, and when I don't treat it for 2 weeks, sometimes the infection doesn't get better. Therefore, you have to treat it for 2 weeks. And so course durations were set down. They were always multiples of 5 fingers in your hand or 7 days of the week. And over the years, some trials have tried to eat away at this by showing equivalence of shorter courses. They almost always show the shorter courses are just as good. But they don't really tell doctors and patients how long an individual person should be treated for and when they should stop. So let me give you an example. This is about the best paper you can find. This was published in the New England Journal last year. The New England Journal is the leading medical journal in the world. Big, well-conducted, large, randomized controlled trial of antibiotic treatment with that drug I mentioned, coamoxiclav, in children with ear infections. And it randomized children to either get a standard 10-day course of treatment or to get a 5-day course of treatment. And the trial concluded that actually the children needed 10 days. The cure rate was higher with 10 days. So the conclusion of the trial is we need to stick with a 10-day course of treatment for the otitis media in kids. The problem is that if you look at the data, 66% of the children who got 5 days were cured, which means if you give a 10-day course and you send the patient away, 2/3 of the children get twice as much co-amoxiclav as they really needed to have. So is this really the sort of data that we should be generating to tell patients and doctors when they should stop their antibiotics? What about this idea of completing the course to avoid resistance? So we did some work a couple of years ago now, led by one of our trainees, Jen Fitzpatrick, to try and understand where this idea came from. And she uncovered that actually if you go back to Alexander Fleming's Nobel speech, you find this extraordinary statement. I know you're reading it yourselves, but I'm going to read it out loud because I love it. It's so great. Mr. X has a sore throat. He buys some penicillin, gives himself not enough to kill the streptococci, but enough to educate them to resist the penicillin. He infects his wife, Mrs. X. She gets pneumonia, is treated with penicillin. The streptococci are now resistant, so the treatment fails and she dies. Who is responsible for Mrs. X's death? Well, Mr. X, whose negligent use of the penicillin changed the nature of the microbe. Moral, if you use penicillin, use enough. Now, I know you're going to be thinking, who's this guy taking a swipe at Fleming? But I would point out that he was fundamentally wrong in that streptococci have never learnt to be resistant to penicillin, but he was also wrong in the generality because he understood an idea that you might think of as target selection. So the idea that you get mutational resistance in the germ you're targeting with your antibiotics, and this may allow the infection to be spread from person to person when they're on treatment or to re-emerge and cause resistant infection later. This is admittedly plausible for professional pathogens like strep pyogenes. It does happen. Probably happens for TB and gonorrhea. To be fair, the solution is not long courses. The solution is adequate dosing and probably using combinations of therapy. He didn't understand what you now understand after me banging on for 40 minutes about it, the importance of commensal opportunistic pathogens. Because what happens when you take an antibiotic is that you get bystander selection for resistance. So all the organisms in your gut are exposed to these antibiotics, or the organisms in your skin, in the environment, and these act as reservoirs of resistant strains, the Staph aureus in your nose, the E. coli in your gut, for the infections you're going to get in the future. So antibiotic exposure correlates very well with resistance in a way that he did not understand. No trial has ever shown, in fact, that shorter antibiotic treatment results in increased resistance. So we published this little analysis in the BMJ a couple of months ago, and I went off on holiday and kind of forgot about it. And it produced what can only be described as a bit of a media storm. It was reported in over 200 newspapers around the world in languages from Russian to Swahili. I was just looking at a few of them last night. Some experts saying this is great, the myth needs busting. Some experts saying keep taking the tablets, reasons to stay the full course. I could be churlish and point out the honoraria this guy received from various drug companies, but hey. Really bonkers things. Why taking fish medicine is a bad idea. I never read that. I don't understand why that's related to it. This is my personal favourite. Feeling better, different from wanting to get pissed. Antibiotic users told. I don't know where all this came from. We were simply trying to raise the idea that syndrome-specific course durations backed up by this false threat that you're going to get resistance if you don't stop when you might be well enough to stop is probably driving antibiotic overuse, and calling for people to start at least thinking about patient-centred antibiotic prescribing in primary care, because that's where 70% of the antibiotics are used. I'm almost out of time. In the last few moments, I want to talk a bit about the major research project that we're involved in this area at the moment, which is called Antibiotic Review Kit Hospital. This is taking up most of our lives in the ID research group in Brighton at the moment, really. So this is a 5-year program grant from the NIHR, National Institute for Health Research. It's a huge collaborative project with people from the Universities of Oxford, Southampton, Brighton. We've got clinicians like myself and Tim Pito, Sarah Walker, statistician, Lucy Yardley, who's a behavioural psychologist, Chris is a GP, Sarah is a health economist. And this trial is trying to find out if we can change the behaviour of hospital prescribers so they will actually stop antibiotics in patients that don't need them. It's a multifaceted behaviour change intervention which involves educating prescribers, a decision aid to help them make the right decisions more easily, some information for patients about why their antibiotics may be being fiddled around with by their doctor, and a process of audit and feedback. to sustain the intervention in practice. And we hope that this will safely and substantially decrease antibiotic use in hospitalised patients and really reduce resistance in the future. This is a huge undertaking. So we introduced the behaviour change for the first time in Brighton in April of this year. I'm pleased to say it went really well. We saw an increase in the antibiotic stop rates on our acute medical unit from less than 10% to greater than 30% in a way that was sustained, at least for the first 3 months we've looked at so far, post the evaluation. We have 3 acute hospitals now starting the intervention in Oxford, South Tees, and then Frimley Park come online in a week or two. The first 5 sites that will be randomising to the full trial will begin in January. And this is to be a nationwide, really, we've got permission to do it in Northern Ireland, Wales and Scotland now as well, a trial which will recruit 1 in 5 of all the acute NHS trusts in the country over the next 2 years to complete recruiting by 2020. It's certainly the largest and most ambitious trial of its size to try and change antibiotic prescribing. And it's hugely dependent on the team locally in each site that's doing it. So this is our wonderful ARK Brighton team. We had a little after-show party. This is Lizzie holding the antibiotic review cake. Lizzie's a junior academic trainee with us. In fact, she was a BSMS student, did her research project with me many years ago, has come back to do ID with us. Jazz, you've already met, more senior trainee now doing AMR work. Vikesh and Sam, pharmacists. Will, a junior doctor in the acute medical unit. This is Nelson, one of our AMU charge nurses. Catherine, Dan, who are acute medicine ID doctors. Without these guys, it would not work. And these people are also crucial in informing how the ARK intervention is going to change and be impacted across the NHS over the next 2 or 3 years. Very nearly there. There are 3 studies that I want to mention in relation to antibiotic resistance beyond ARK. We have a European-funded study called CASE, which Jazz works a lot on, which is developing recommendations for how studies should actually be designed to tell us how to actually use antibiotics better to get good outcomes in patients. ARMORD is a study that I'm involved with through Oxford, which is trying to develop individual patient measures of resistance so we can use them in clinical trials to assess impact of antibiotics on patients. In collaboration with Mike Hopkins at the Science Policy Research Unit here at Sussex, he's running a European stakeholder appraisal trying to understand which diagnostic tests for antimicrobial resistance will succeed in clinical practice. Mike's sitting just over there. He's got a website and he's trying to get stakeholder engagement, so he'd love to talk to you all after the talk. I've chosen to make this talk all about antibiotic resistance and the healthcare associated infection stuff because that felt like the most topical thing to be talking about to you today. But I want to finish the research bit at least by acknowledging these guys, because a separate theme in the research here over the last 10 years has been an ongoing theme of sepsis immunology research, which has essentially been led and taken over first by two fantastic postdocs, first Amanda Taylor and secondly Stefano Caserta, and they've produced a series of great papers looking at how we can develop biomarkers of infection based upon host immunological responses, and this is really their own work as well, so I shouldn't really be talking about it. So I've told you a story of trying to combine clinical practice, training, research in a way that tells us something about the bugs, tells us something about the patients, tells us something, if it buzzes along, about the treatment the patients get, and tries to bring all these things together to improve the prevention, diagnosis and treatment of infection in modern medicine. I've tried to thank all the people involved as I've gone along. There's one very important person I've not mentioned who's my line manager for the last 10 years, who's Kevin Davis, who I should point out for the first 5 years ignored the fact I was doing none of this and was doing a lot of clinical practice and training on the basis that I had to get these things sorted out in order to do some research. And I'm extremely grateful for your patience and confidence that we did ultimately get on and do some research with all of this. Finally, I've mentioned Katie once already, finally and fundamentally, my wife Katie, who's been my strength and support throughout for the last 18 years. And I wouldn't be able to do anything or be anywhere without her. We moved to Brighton when Ewan, who you heard from a few moments ago, was 6 weeks old. That's Aaron, who you've not spoken of, but he's there, was clearly trouble. And she has supported me through all of this and sustained her own career through the birth of Polly, who you heard from, arrived there. And here they are now, my ongoing reason to get out of bed every morning if only to make the tea. So thank you very much for your attention. I hope I haven't gone too far over time. I have to finish with these words. May I now present Professor Malcolm Reed, Dean of Brighton and Sussex Medical School, to conclude the proceedings. Thank you.